Hello, Professor. Today I want to introduce the Lecture 6 summary. I'm today's presenter, Jiajun Jiang. And here is the agenda. I will start with the type of branch, and then is branch predictor, and what kind of hardware do we need in the branch prediction, and then is static branch prediction and dynamic branch prediction. So the type of branch. The branch can divide to different branch. The first one is conditional branch and second is unconditional branch. The branch predictor is to prevent conditional branch because before the ALU, we cannot know the result, so we cannot decide which address should jump to. For example, if else branch, if conditional A, we go A, else So before we know the result, it will cause branch hazard. So we need branch predictor to prevent this situation. Unconditional branch is a branch already know which address should jump to. So we don't need branch predictor on this kind of branch. And the backward branch is target with the lower address, for example, loop. Forward branch is target with higher address. And branch predictor. There's no 100% correct branch predictor. So there's still have chance to encounter the control hazard, and there's a several solution for branch hazards. The number one is stall all the pipeline, which is the easiest but very worse in the performance. And the second is branch prediction. Third is do other things. Four is eliminate control flow instruction. The last one is do every possible way. It's like if there is a condition and it will cause 3 results, for example, so we will calculate all the possible. We will calculate all these 3 answers. This method needs multiple path execution. But this lecture we will focus on branch predictor. Branch predictor need add some hardware to support it. The number one is branch history table. And number 2 is branch target buffer. This is a little memory to store the address. And the last one is mispredict recovery mechanism. Branch history table is a small memory from branch address. This memory includes 1 bit to indicate this branch jump or not jump. Branch target buffer is a cache used to read the destination of each branch jump. In the if stage, use the current PC as the index value to find the destination of the current branch in BTB. If it found it, means the instruction is a branch, and it will predict it will jump. So if the branch jump, it will be executed normally. But if the branch does not jump, then we'll flash the previous instruction and delete the corresponding PC in BTB. What if not found in the BTB? Then it will continue as usual. Then if the branch jumps, it will add the destination address to BTB and flash all the previous instruction. But if the branch does not jump, it will execute as usual. And then there's 2 ways to do the prediction. The first one is static branch prediction. Another is dynamic branch prediction. I will introduce all different methods sequentially. Let's start with static branch prediction. The static branch prediction is that cannot be dynamically adjusted based on branch history, input, and results. So there's several ways. Always taken, obviously, it means every time it encounters a branch, it will jump. On the other hand, always not taken means every time it encounters a branch, it will not taken. The reason why always taken have much higher accuracy than always not taken because the loop. We have so many loop in our program, so if we always taken, we can run the loop correctly. But if it is not taken, the accuracy only 20% to 40%. And then is profile base. The profile base use the compiler to collect runtime information to decide whether to jump to a branch. So the accuracy depends on the data. And the program-based prediction. The program-based predict branch less equal 0 as not taken. It does not require additional profiling. but the heuristic may not be representative. The last one in static branch prediction is programmer-based. The programmer-based, it is up to the person who actually write the code to give the information about whether the branch jump. This does not require advanced profiling and analysis, but require the support of programming language, compiler, and ISA. So the advantage of static prediction are lower power consumption and low implementation cost. But the biggest disadvantage is that the prediction result cannot be changed during the runtime. Because if computer mispredict the branch, it will cause a lot of performance to fix the mistake. So modern CPU usually use dynamic prediction to acquire better accuracy. So let's start with the dynamic branch prediction. The advantage of dynamic prediction is that it can be dynamically adjusted based on branch history input and result, and it won't require static profiling. The disadvantage is that it requires additional hardware to support it, and the delay will be longer. The last time prediction means the predictor will choose the last time result to predict the next result. So it is pretty good in a loop for the loop t and n won't change a lot. So we can see the picture. If the result is t t t t n n n n, so it will acquire the accuracy is 90%. The accuracy for loop with n interaction is n minus 2 over n. So we can see if the loop is tn, 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 so it will acquire 0 accuracy. So we can see the picture. If the predictor mispredict, it will change to not taken. And then if it mispredict again, it will change from not taken to taken. And then is 2-bit prediction. The last time prediction is 1 bit, but this is 2-bit. The method in 2-bit prediction is it will not change the result immediately. It will use the last 2 times to predict the result. The core is that the direction of the branch instruction change occasionally, and the prediction value will not change immediately. Each branch corresponds to 4 states: the strong taken, weakly not taken, strongly not taken. And compared to the next example, the TTTT, we will acquire 50% accuracy. But the accuracy is still really bad. The accuracy effect. Assume there's a 20 pipeline stage and 5 while fetch, and assume there's a 20% instruction is a branch. So how long does it take to fetch 500 instructions? We can see how to calculate the question. So we can see if the predictor is 100% accuracy, it only takes 100 circles. But when the accuracy lower 5%, it will need 200 circles. If the accuracy is 90%, it will use 300 circles. So even the prediction accuracy is 95%, it sounds really good, but it still needs double time circle to execute the program. So we have 2-level prediction. If a branch will consider the previous result, a predictor we call is global predictor. If the branch depends on itself, we call the predictor is a local predictor. In global predictor, we need a register. It is need to record the past execution state of all branch instruction in the program. We call the register is global history register. And we can see there's an example on the left part of the slide. If the condition 1, and then if condition 1 and condition 2. So if the first branch is not taken, the second branch will not taken also. And the right part is if both B1 and B2 are executed, then B3 will definitely not be executed. This pattern cannot be discovered by relying only on local branch history, because the local predictor only depends on itself. The two-level prediction, you can see from the picture above why it is two-level. The first level is a set of BHR with a bit width n bits, recording to the result of the branch n times in the path, using branch PC addressing. Second level is using branch history register to address the pattern history table. The size is 2 power of n times 2 bits. If the branch result is tn even alternatively, and the branch history register is 2-digit, then the pattern history table will have 4 entries because the number of pattern history table need the 2 power of n bits. The value of n is BHR. So if branch history register use 3 bits, so the pattern history table will need 8 entries because 2 power of 3 is 8. And then is G-share. The disadvantage of the branch prediction method is that if the GHR have same value corresponding to 2 different branch instructions, then the 2 branch instructions will share the same count in the PHT, so it will cause a conflict. In order to solve the problem, you can still perform certain processing on the PC value and GHR, such as bit splitting and XOR, and use the proceed result to address the PHD. So even if 2 different branch instructions correspond to the same GHR value and will not correspond to the same saturation counter in PHD, avoiding conflict. And is the notation of the n. The n means the number of previous branch correlated, and the n is number of bits for prediction. So if the n is 1, means use the outcome of the previous 1 branch execute and use 1-bit branch predictor. So the original 2-bit counter would be the 02 predictor. And how many bits do we need for the predictor? The formula is 2 power of n times 2 power of t. And then is temporal correlation, which is local predictor. In this method, a register used to record the past historical state of branch instruction. When this historical state is very regular, it can provide a tool that can be used for branch prediction, such as register is called branch history register, which is BHR. So we can see the example is last 11-bit branches is 0001, 0001, 000. So when we use local predictor, obviously we can know the next one is 1. The main difference between global predictor and the local predictor is the local predictor. Each branch has its own local history register. And the last one is hyper branch predictor. Some branches are suitable for predictor using local history, some suitable for global history, and sometimes use the 2-bit counter is already enough. So the ideal of hybrid branch prediction is to use multiple branch predictor and then select the one which is the best and most suitable for the branch. The advantage, it can obtain better accuracy. The disadvantage is we have to add an additional selector to choose which predictor to use. So we can see in the picture, the blue one is the local predictor and the yellow one is global predictor. So we can combine those two to obtain better accuracy, and this predictor is called hybrid branch predictor. So here's all my presentation. Thank you, Professor.